Objective 4-4 deals with momentum. In Goal A, we talked about momentum, and the equation for momentum is P, which is momentum, equals mass times velocity. So now in Goal B, we're going to apply the conservation of momentum. So all this tells us is during a collision, momentum is conserved. Now there's two types of collisions. So for this first example, example number 1, we're going to look at an inelastic collision, meaning two objects collide and they stick together. So we have a 5 kilogram object going 12 meters per second east, and it collides with a 14 kilogram mass at rest. What is the speed of the objects after the inelastic collision? So we're going to use this MVP chart. Now the whole point of this MVP chart is basically to help us organize the information we have and help us figure out what we're trying to solve for. Since we're looking for the speed of the objects after the inelastic collision, we are solving for the final velocity. So we're solving for this box over here. That's our ultimate goal. But we have to fill in everything else first. So we look at what we have. We have a 5 kilogram object. So we'll call that object 1. So I'm going to call that 5 kg, and we know that it's going 12 meters per second east. Now if you think of a compass, east is to the right, so I'm going to call that positive. Remember, velocity is a vector, so it does have a direction, so we got to be careful with that. For object 2, it's 14 kilograms, and it starts at rest, which means that its velocity is simply 0 meters per second. So to find the momentum, P, of each of these objects before the collision, we're going to use our equation, P is equal to mass times velocity. So 5 times 12 is 60, and the units for that are kilogram meters per second. And then for object 2, 14 times 0 is simply 0 kilogram meters per second. Now the total initial momentum of the system, so the left side of this chart, this is before the collision, the total we have to add the two up. So 60 kilogram meters per second plus 0, well, that's just simply 60 kilogram meters per second. Okay. Now this law, this conservation of momentum, the whole point of using this chart and applying this law is to show us that the momentum is conserved. So the momentum before the collision equals the momentum after the collision. So I'm literally going to transfer that 60 kilogram meters per second to the right side of this table because that momentum is conserved after the two collide. Now, because this is an inelastic collision, that means that the two objects stick together. So if you have a 5 kilogram mass and a 14 kilogram mass, to get the total mass, well, now essentially we have one big hunk of mass that is 19 kilograms. So to solve for V, we know that P is equal to M times V. So 60 equals 19 times V. So really our velocity comes out to be about 3.2 or so meters per second. So that is our final answer for this inelastic collision. Now note also that the velocity is positive, which means it's going to be headed east, so in the same direction as the 5 kilogram mass was. And it should make sense conceptually that the 5 kilogram mass was traveling at 12 meters per second. It collided with something that was at rest. So think about if you run into something, it's going to slow you down. You're not going to speed up. So it does make sense that the 5 kilogram mass initially going at 12 meters per second slow down to 3.2 meters per second. Now one last point I want to make. When we look at this chart, for inelastic collision, we can add the masses to get the total mass here after the collision. We add momentum to find that total momentum. However, we cannot add the velocities. Even though velocities are vectors, for the sake of these collisions and these problems, we cannot simply add velocity to solve for velocity. We have to use momentum equals mass times velocity.